So, thanks again. Sorry about the delay. I don't know what's going on. Everybody's amps upstairs are sucking a lot of juice out of the building or something. All right. Let's get the show on the road here. Make sure I'm on. I'm going to be doing, since this is from the cuff, there might be a few technical snags here and there, but I think we'll be able to get through this. So it is 5:23, so we'll try and wrap this up in about an hour. So first off, my name is Jeff Merkel, and I'm not a professor, but I'm an instructor at the University of Colorado, Denver. I teach in both physics and in the recording arts. I teach physics and music and sound, and so actually I think there's a couple students in the class here, so welcome. This is the class this is kind of a condensed version of the class that we do in physics. And then I also teach in recording arts, and I teach a class called Studio Maintenance and Calibration, so I do a lot of obviously maintenance and calibration, but I also do things like audio production, how to record bands, how to do sound for film, and how to do that kind of stuff. So it's kind of like I live in this techie world where I get to do a lot of the science and a lot of the art behind all the stuff that we work with here. But I also run a couple other companies. Professionally, besides teaching, I run a studio called 8 Houses Down. We're primarily a punk rock studio because that's what I played through college. But we do music, but we also do audio post, and it's a mastering studio. So I'm the mastering engineer, and I've been mastering engineer for about 12 or 13 years. I'm not exactly sure in there; it's a little fuzzy when I actually officially started. But I master full time, and so that's like a good 60% of my income is being a mastering engineer. So I do that a lot. And then I also run another company called Merkel Acoustic Research and Design, and that came out of my master's work, which was on loudspeaker design, and more specifically, transmission line loudspeakers. So that's kind of my thing. And so I've started up a new company called Merkel Acoustics, and that we do a lot of stuff. Besides speaker stuff, we also do it's just general raw research, where we're going to do stuff like sonar, cochlear implants, anything to do with audio. So that's kind of where I come from, and just who I am, and where this is all going from. So what we're going to do, this is, again, for any of my students in the place, this is my classic start. This is what we're going to talk about today. When coming up with this talk, and I apologize, I do speak very quickly. Sometimes we have a lot of material to cover here, and I'm a little caffeinated. So usually I have a soda up here too, which just makes things even worse. But we'll try and keep it pretty mellow today. But what we're going to try and do today is I want to talk about frequency, wavelength, speed of sound, interference, reflection, diffraction, and standing waves. Chances are we're probably not going to have time to get standing waves, but unfortunately, because that's the good stuff. That's some of the good stuff. But when coming up with this, I had to decide at what level should we do this talk. But so pondering it for a little bit, I thought, well, I think most people have a very good intuitive understanding of what's going on. When you're walking around in the rooms upstairs or in any of these halls, you're listening to music, and you're listening to the music, but you're not listening to what's going on with the sound waves. So what I wanted to do is take a step back and look at the fundamental, what's going on with sound, what's going on with the air molecules. And as much as anything, what I want you to walk away with today is getting an idea of wavelength and how wavelength, the length of the sound wave, affects your sound. Now that has everything to do with loudspeaker design, with room acoustics, with auditorium acoustics, with this room, in every respect of our audio lives, this concept of wavelength is built in. So that's kind of what I want to go. But we're going to start with some of the fundamental stuff. And yes, I know this is some of the stuff is pretty fundamental, but some of it might be a little rusty. And if you haven't seen it for a while, that's okay too. And so it's not meant to be like crazy technical, but I want you to walk away with some pretty cool trivia you can impress your friends with next time you're at some gathering or dinner or something like that. So let's dive right into it. So let's talk about this concept of frequency. So frequency, is there any way I can dim this one just a little bit? I don't know. I guess not. Never mind. There's no spots. That's okay. Don't worry about it. It's all good. So let's talk about this concept of frequency. So frequency, we hear that term all the time here. When we're looking at spec sheets, when we're talking about frequency response, when we're talking about frequency of hearing, when we're talking about anything, especially in this situation where we're talking about sound, we use the term frequency. But what do we mean? What's the frequency? What's going by there? Well, the name itself, frequency, is something that we're pretty intuitive with. Frequency means how frequent something goes by. How many times, it has to do with time, right? So when we talk about sound, and usually in physics, in basic physics, we use the sine wave because it's pretty easy to work with and easy to describe. But truth is, when we're listening to music in any of these rooms or at home or your home theater or whatever, or even playing on a guitar, this concept of frequency is a complex waveform, but it doesn't matter what the waveform looks like. And I didn't want to get into complex waveforms and harmonics and formants and all that kind of stuff today. It gets a little outside the scope of what we have time for, but it is very cool stuff. But this idea of frequency, what it is it's one complete cycle. So in other words, if we're thinking about it, and I use speakers as an analogy all the time. So I actually happen to have a speaker right here. So what we're talking about when we talk about frequency, what's happening, especially if I'm doing something like, say, a sine wave. A sine wave now has a nice, simple sine curve to it. Now when we say frequency, what it's saying is in the case of a sine wave, the speaker is going to go out, in, and back to its normal position. That's one cycle. So that's what it's doing. We call that, I guess, just one cycle. So how many cycles per second that goes by? We could say cycles per minute. We could say cycles per hour. But in most audio terms, and if you're talking about something like black holes or some other physical term or physical phenomena, you may use a different type of frequency. But in normal audio, we use hertz. Now, hertz, it's defined as cycles per second. So how many times it goes through a cycle. Now, again, I'm using the sine wave as an example, but you can use anything, and it means how many times per second this is going. So I just wanted to throw out there. And so when you're watching your drivers, especially on the big boys, when you're seeing the huge woofers going, you can actually watch the cycles going through. And so it's going through its entire motion. Now we don't usually listen to sine waves for listening demos, but you get the idea. You can actually see it going through its complete cycles. So so what we need to do is knock out some of these fundamental definitions before we start talking about some more of the complex stuff. And frequency was the first one I wanted to hit on. Second one is velocity. So velocity is distance per time. And that's something we also have a very relatively intuitive understanding of. Well, not everyone. I drive a lot less than I used to. But we have an idea of miles per hour. How much time how much distance did you cover in a given time? So, or you could talk about it in feet per second, in meters per second, you can think of anything. Anything that has a distance and a time. Now, truth is, in physics, we use velocity implies direction as well. But for today's talk, we're just gonna talk about it essentially saying it doesn't matter which direction, because you can have a negative velocity. This is negative velocity. If I were talking this is positive, then this would be negative. So, but for today's talk, we're going to use this velocity as just a rough, as meaning essentially speed. That's how fast per time. So v equals d over t. Now I apologize. I said in the description when I was writing the thing for this that this is not going to be a mathy talk, but I lied a little bit. So there's going to be some math in here, but it's all good, and it's for a good reason, I think. And again, because the bottom line is what I want you to walk away with is understanding wavelength and how that relates to what's going on here. Now length is just, it says there's numbers involved there. And so we want to talk about those numbers. So let's talk about some velocities. Let's talk about the speed of sound. So this is a jet breaking the sound barrier right here. So the speed of sound is 343 meters per second. You can't see my little disclaimer down here, but 343 meters per second, or 1126 feet per second. In America, a lot of people think about 1126 feet per second, but coming from a science background, everything I'm going to do today is in meters. So if you're not too fond of the metric system, I apologize, but that's how I think, and I have to stay in the metric world for this sort of thing. But with this saying, the speed of sound is actually a little rough. So 343 meters per second, plus or minus. It depends on pressure and temperature. And so this definition, 343 meters per second, is at 20 degrees Celsius at sea level. So things do change. And so when we go through the calculations, it's a little like crude, but it works. All right, how do we use this? This is kind of a classic example of how do we use feet per second. It's a little washed out, but it's a very, very cool picture of lightning here. And the classic idea is you see lightning strike. Now, light is much, much, much faster than the speed of sound. So we can, and for all intents and purposes, we can consider the speed of light instantaneous. For all human, normal perception ideas, it's instantaneous. Now, there is, of course, when the light flashes, it does take time to hit you, but we can't perceive any of that. But we can perceive the speed of sound. So when the lightning strikes, and we start counting, and the classic, I think a lot of the times the classic one is people think it's a mile per second, that when you see lightning strike and then you hear it. So let's take a look at this example right here. So you see lightning strike, you see flash, and then hear thunder 3 seconds later. Should you be worried? Well, let's do some math.
3 seconds?
Yeah, 3 seconds. So velocity, using that equation I just had up there, is distance divided by time. So let's do a little bit of algebra real quick and rewrite this thing. So it's distance, because that's what we want to find out, is how far away this lightning was. That's what's really a paramount concern to you, is velocity times time. Now, if you're not comfortable with if it's been a while since you've done algebra, you're just going to have to kind of take it for rote. But we're just doing some quick algebra, and unfortunately I don't have time or a whiteboard to go through and talk about it. But so we take our velocity times time. So we take 343 meters per second times 3 seconds. That ends up being about 1,000 meters, or 1 kilometer. Should you be worried? Probably not too much, but stranger things have happened. I mean, I've been, oops. So you probably don't have much to worry about. You still could be struck, so you're probably going to be okay, but there is potential of getting hit. And I've had the unfortunate experience of almost getting struck before, and it was a lot closer than 3 seconds. And so I've been there before, and hopefully you don't have to deal with that very much. So, all right, how are we doing here? So, okay, that's what I wanted to do right there, because the speed of sound plays into for the rest of the talk. And I call this, well, actually, one of my professors that I took calls this 3 a.m. knowledge. I want you to commit that 343 meters per second. If you're more comfortable working in feet, 1126, that's okay. Commit those to memory, and it's called 3 a.m. knowledge. If I were to call you up at 3 in the morning, and you're like, hello, I'm like, hey, what's the speed of sound? 343 meters per second. Click. That's what I want you to know. That's one of those ones that's like cool. You actually can know that having 3 a.m. knowledge. This is one of them. This is one of those things that it's cool to have, and you actually start using this thing quite a bit. I use this 343 meters per second all the time, especially these equations these few equations that I'm going to be throwing up here. I use those things all the time. All right, let me make sure I'm not missing anything here. The other important thing to know about the speed of sound is that it's frequency independent. Now, we're not going to have time to go into huge detail in this class, or from this session, but when you start thinking about it, you're like, well, do low frequencies travel faster than high frequencies? They don't. And we could go through and do a number of tests to prove this, but if you think about, say, a marching band on the field. Now, you may have some distance between you, like the sousaphones in the back and maybe the piccolos in front, and that may cause some difference. But the truth is, all frequencies travel at the exact same time. So, in other words, frequency is medium dependent. It's not frequency dependent. Or the speed, I'm sorry, the wave speed is medium dependent. So if I talk about in terms of an acoustic guitar here, and the wave on a string, it has to do with the concept of the weight of the string. So we'll come back to the guitar here in just a minute. I'll pull this guy out in a bit. So that's just one of the little piece of trivia as you're thinking about there, that all frequencies travel at exactly the same speed in the same medium. So it's medium dependent. The higher the density, the faster it moves. Think about water. Sound moves much faster in water than it does in air, and that's because air is much more dense. And so it's a function of the medium, not of the frequency. All right, so let's start talking about waves. And then what we're going to do is we're going to tie in some of this speed stuff in here and we'll start pulling out, this whole beginning stuff. There's not a whole lot of demo stuff. We'll start dealing with demos here. When we talk about waves, there's essentially two kind of waves that we deal with in sound. We have transverse and we have longitudinal. And we'll talk about a little bit about what each one of those are. Let me see. Make sure I don't pass on anything. So the first one we're going to talk about is transverse waves. Transverse waves are like water waves. Now, what a transverse wave is, when the wave motion is perpendicular to the wave propagation. Sounds real technical, but what's happening, what I mean by that is that a wave is moving up, and the wave is oscillating up and down, but moving in this direction. So you could imagine like a water wave. A water wave, you throw a pebble in a pond, the waves, we can see them, we see the ripples spread out, and the waves are going up and down. The wave amplitude is up and down, but the propagation is, at least in the case of a pebble, is in a circular pattern. So where else do we see transverse waves? We see them in drumheads. A drumhead has a transverse wave. We have transverse waves on a wave on a string is a guitar. This is where we do one. So what we see here is the string is moving back and forth, and it's kind of hard to imagine it. And we're probably not going to have time to get too far on the standing waves business. But the standing wave the wave is moving back and forth in this direction. Now, when you think about like a rubber band, when you pluck a rubber band, or when you pluck a guitar string, in your mind's eye, you're watching the string go back and forth. You're not really imagining it as the wave traveling back and forth, but in truth, it is. It's actually traveling to and fro along the string. Another place we run into it, cone drivers. This is where we don't want to see them usually. We like as loudspeaker manufacturers and driver manufacturers, we try really, really hard to make those things not have standing waves on your driver cone right here. But that's what we call cone breakup. When the frequency gets high enough, it starts to cause standing waves and surface waves and transverse waves on your cones right here. And it happens both in tweeters and in woofers. But we try real hard to make those so they don't happen. And there's all sorts of techniques for that sort of thing. So we do see transverse waves quite a bit. But for most of the day, what we're going to talk about are longitudinal waves. So kind of opposite of what I was just speaking out just a minute ago, you can kind of figure out, with a little deduction, you can figure out if I'm saying that a transverse wave is perpendicular to the to the direction of wave propagation, a longitudinal wave, it moves in the parallel direction of wave propagation. Now these ones are a little trickier to imagine, and so we have some kind of a classic analogy here. We'll use this one for just a moment, but the slinky is a pretty good example. I need a little bit of help here. Can you grab one end of the slinky for me? Just hold it. So what we have here, and we'll set it down on the thing. Actually, this will work pretty good on here. Sorry if you guys can't see this, but we have some animations here in just a moment. Now what I'm going to do is I'm going to pluck this thing, and you can see it travel down to his hand, and actually reflect off of his hand and come back. So what we're seeing now is that the wave, this wave compression, this compression wave, thank you. This compression wave is traveling in the same direction as the wave propagation. This is exactly how sound waves work. So let me pull up. I've got some simulations here that are kind of fun to look at. All right. So what we have here, we've got this. When we're talking about air here, we've got this squishy stuff around us. Air is very squishy, and what it's made up of is just a bunch of air molecules: nitrogen, CO2, oxygen, hydrogen, all these different molecules floating around us. And they like to stay apart from each other, but they have this ability to get pushed together for a little while. And they also have the ability to spread apart from each other. So what we're going to do is we're going to force these waves, we're going to force these molecules to get close together for a little while. And then they're going to propagate out. So actually I have one more animation here. Let me, there we go. So what we're going to do, oops, let me get back to there. Let me pull up this other animation here. It makes it a little more, drives it home a little bit more. So these animations are from CU Boulder, the physics department there. It's huge. All right, so what we have here is we have a speaker that's moving back and forth. And what we can do is if we imagine that the air molecules are white. So what they're going to do is they're going to evenly distribute themselves around the air here, and we'll call that ambient air pressure. But what we're going to do is we're going to mess that up with some speakers here, and we're going to squish those air molecules together. And as they get squished together more, they're going to, in case of this, it's going to look more white. It's going to be whiter. But we're also going to do something else. We're going to pull the speaker back. And this is the weird thing. It's a little more counterintuitive. But when I pull something back, it sends out a negative wave, a wave that's like not spread out. So instead of like imagine what intuitively we might think it sucks it in, but that's not what happens. When the speaker pulls back, it sends out a lower than ambient air pressure wave out, and in this case, it's going to look darker. So what's happening is these air molecules are pushing onto each other and propagating out. Now sound is an energy. It's an actual energy form. It's coming from my vocal cords actually into this mic, and electrical energy is pushing it out of the speakers here. So what we're doing is it's squishing the air molecules and they're pushing them out. But what's interesting is that the air molecules aren't moving. Well, they're wiggling back and forth, but they're not propagating out. So what we can do with this animation, is we can look at this, and this is what the air molecules are going to look like. You can see a few of them. They're kind of hard to see, but if you look at this one that has an X on it right here, you'll see that's oscillating back and forth, but it's not actually traveling. So also you can think about this. I use water waves as an analogy. They're transverse waves, but we can use those as an analogy. You think about a duck floating on a pond there, or even in the ocean or something, and a wave goes by. The duck isn't hauling, unless you're surfing, which is a little different. But if you think about a duck and a wave passing by, the duck sits in the same spot. And same thing happens with air molecules. This is also why if you were to like a loud concert, you're not like getting blown away. I mean, the classic example was that Max L did that thing for a while, where They're being blown away. That was their campaign. But truth is, the air molecules are just moving back and forth. I have a candle demonstration here, but we're running a little behind. So it's pretty cool to see how this stuff works, though, and it's actually it's pretty mesmerizing to watch it for a while. But what we're going to do is what we have is whenever the speaker pushes on the air, we call that a compression wave, and whenever it pulls back on it, we call it a rarefaction. It's a little weird word, but it's called a rarefaction wave. So we have this combination of compression and rarefaction waves that go out. Now they're very hard to draw. Typical compression and rarefaction is, alt-tabbing, is a little difficult to draw. If we look at this, we kind of see a transverse wave here, and we see a longitudinal wave, because we can see that all the air molecules are pressing up into each other. But this is a bit difficult to draw sometimes. So typically, we'll draw transverse waves, but what we're plotting is longitudinal or compression waves. So it could either be done as voltage or as air pressure or as any kind of amplitude function. Okay, so and that's kind of the heart of what we're going to talk about today is these compression and rarefaction waves. So when you're thinking about what's going on with these speakers, that's what's going on. They're pushing, and then again, it's weird. When they pull back, it sends out a negative wave that goes out. When I say negative wave, a lower than ambient air pressure wave. It's not like there's zero air pressure. It's just lower than ambient air pressure. All right, here's one more bit, 3 AM knowledge. B equals F lambda. Now this one looks all scientific and cool, but it is really cool. This is fundamental to all waves. So if you're talking about light, sound, anything that has wave-like function, but we're going to use it for sound today. And the V is velocity in meters per second. Again, I'm using meters per second. Frequency is in hertz, and lambda, the lowercase Greek lambda, is wavelength in meters. So we have all the algebraic variations of this equation here, but we can see that we could see a bunch of different versions of this. If I give you two of these, if I give you two variables here, you can figure out the third, basic algebra. But when we're talking about sound and air, we know this V. 3 AM knowledge. What's the speed of sound? 343 meters per second. So all you need to know is frequency, and you can find out wavelength. Or I can give you wavelength, and you can find frequency. And that's what I want you to start to relate here. So let's talk about in terms of human hearing. We can hear from 20 hertz to 20,000 hertz, typically. I can't hear to 20,000 hertz anymore, unfortunately, and most of us probably can't at this point. It's just, you probably haven't been able to hear 20,000 hertz since you were about 7 years old. Sucks, but that's nature. So what we're going to do is we care about this range right here. And let's talk about this in terms of wavelength, though. So I've given you frequency here. Let's see what this is in terms of wavelength. And this is where we're going to start to see the effects of rooms and how speakers are designed. So let's look at this first question. What's the wavelength of 20 hertz, the lowest frequency we can hear? Well, we go through V equals F times lambda. We do a little algebra. Lambda, which is wavelength in meters, is V times F. Now, what do I mean by wavelength? The length is exactly the wavelength is it's the length of one cycle. It's the time. It's the distance of one cycle in air. So let's go through this. 343 meters per second times 20 hertz. Now this is actually cycle. Remember, hertz is cycles per second. Yeah. So I wrote 344. Different texts use different ones. When I started doing acoustics, I learned it as 344, but then most of the stuff I teach with now uses 343, so I switch, but sometimes I fall back into old habits and I use 344. So 344 divided by 20 hertz gives us 17.2 meters. That's huge. I mean, if you're more comfortable thinking about it in terms of yards, that's okay. It's pretty close. You can think about it as 17 yards, but 17 yards for a 20 hertz wave, that's massive, right? That's like longer than the length of this room, this direction. So let's think about that for a minute. Like, just that's again, this is the kind of the core of what I want you to feel. Is a 20 hertz wave is 17.2 meters. That's huge compared to you, and it's huge compared to the speaker. All right, let's look at another example. What's the wavelength of a 20 kilohertz sound wave? So this is the highest frequency that we can theoretically hear. So we go through V equals F times lambda. I always start with this equation. This is there's all the algebraic variations, but I always start with this one. Lambda equals V divided by F, and lambda equals 344 divided by 20,000. Remember, 20 kilohertz is 20,000 hertz. And we ended up with 0.0172 meters. How many centimeters is that? 1.72 centimeters. So that means 20 kilohertz is this big. So that's a pretty huge difference. Think about 1 kilohertz or 20 kilohertz versus 20 hertz. Huge. Those wavelengths are massive. Well, let's reel it in. Instead of talking about all the way out and all the way in, let's do one more, and let's talk about 1 kilohertz, because that's one that we actually use for measurement and that we actually run into. 20 hertz, it's in 20 kilohertz. They happen in our music, in our reproduction, but for the most part, we care about what we hear in the mid-range. 1 kilohertz, I'm just going to, without going through all the thing, it's 34.3 centimeters. Yeah, about that big. So we're talking about like most of our mid-range we hear is going to be about here to here as far as wavelengths go. Now this is going to get pretty interesting. So this is kind of what we use as a reference for when and this highly influences acoustics and influences speaker design. Speaker baffles. We've got the ATCs over here. We've got some Genelecs here. We've got our JBLs up here. Now this wavelength size versus driver size is going to come into play quite a bit. We're doing on time here. All right. So what I'm going to do is I'm going to shift gears, and we're going to come back to that. But let's talk about another interesting property, a property of waves, and that's interference. Now, interference implies that we have 2 sound sources. And to me, this is where things start getting pretty interesting. So what we're going to do is we're going to take, and I use this is a pond with some ripples in it. And what we actually are seeing is the light version or the visual version of constructive and destructive interference. When we drop a pebble in this, I think it's sand underneath there, we see these really light rings, and you can kind of see these dark rings going on too. So we have some constructive and destructive interference. Constructive interference is when we have 2 wave sources that are in phase with each other. So I'm going to take this yellow wave on top and this blue wave on the bottom, and we're going to sum those 2 together. Now, waves have an interesting property in that they're additive. And so if I take the amplitude of this one right here and the amplitude of that one right there, and I add those together, they double. Well, in this case, they double because they're both the same amplitude. If I took a smaller one, it would just add to the top one. And the same thing goes on the bottom. So this is what we'll call ambient air pressure, and then this is maximum compression wave, and this is the rarefaction. This is the minimum of air pressure in there. And when I add the 2 of those together, we get a very big wave. So yellow and blue makes green. It's hard to kind of hard to tell, but this is green. So what we can see here now that my wavelength, or my amplitude, in fact, has doubled. In terms of sound, we perceive that as it got louder. So in the slide before when we were using light, we perceive it as brighter or darker. So what we get here is a much brighter or much louder as far as speakers go. Now, what happens if we add 2 of them that are out of phase with each other? Oops, you totally cannot see that. Wow, that's really dark. So there's a red one. So you're going to have to follow my hand here and see where it goes. It goes down here, up here, and down, and back. So it's opposite. It's in other words, phase flipped from this one. And that's what we mean by phase. The phase is 180 degrees out of phase, or phase, it's absolutely out of phase. And when the 2 of those sum together, we get nothing. So I'm sorry that this didn't show up very well. But it's supposed to be flattened out. So and we perceive that in terms of sound. When two sound waves are out of phase with each other, they cancel each other out. This is how noise canceling headphones work. They take the incoming sound, they phase flip it, and feed it to your ear. And so by the time it gets to your ear, it completely cancels itself out. Pretty cool application of the technology. So, and that's doing it. So again, I'm using sine waves here, but you can use complex waves. You can use any kind of waves. So let's take a look at an example where we might have 2 sound sources, and what happens with that when we have that going on. Okay, what I have here is my kind of dorky-looking dude here. He's listening to some speakers from 2 sound sources, and we can see. Where's my laser pointer? That amplitude's all the way up. Move them away here. What we're seeing here is we have our compression. We'll call the white ones the compression wave, and the black ones rarefaction waves, and they're starting to interfere with each other. And as they come out, they're adding to each other along this line, and along this line, they're canceling each other out. So in other words, they're adding to each other here, constructively interfering with each other here, and they're destructively interfering with each other here. What does that sound like? Well, let's listen. So let me move this up to 1,000 hertz. Okay, let me make sure I'm not going to tear anyone's head off, volume-wise. So I've got these Genelecs hooked up to this, so we should be able to hear this. I didn't turn, let me see. Are these on? Make sure that these guys are. Oops, nope. Don't want to turn anyone's head off. It's a classic thing. You turn everything all the way up. What's wrong? Oh, here it is. I used to be a live engineer. I was a live audio engineer for a number of years, and when I was learning how to do that, that was a classic mistake I made way too many times. It's a rookie mistake, but bad news. Come on. Okay. Uh-oh. Sounds like I'm plugged into here. Okay. So it's pretty annoying to listen to. This is a sine wave. So what I want you to do, you're going to plug one ear, and you're going to move your head around and move side to side. And what you're going to be able to hear is going to be able, well, just do it. That's always fun. It's like everyone, like wheatgrass waving in the wind. It's way fun to look up from the side. So did you hear it? Did you hear it getting quieter and louder? That's that interference. That's that constructive and destructive interference. Now this is the rub. I mean, this is something that like we don't brush it under the table, but this is a very, very complex phenomenon that's happening in every single room that goes on upstairs. So it's also happening from, if we're in the crossover range, it's happening from this speaker to this speaker. So 1 kilohertz is probably below the crossover range of this. It's probably crossing over around 3 kilohertz. But if I play 3 kilohertz tone, that means some of the woofer here is playing 3 kilohertz, and some of the tweeter here is playing 3 kilohertz. So you get these, we call them lobes. And this is at just one frequency. So when I start changing frequencies, we start getting, so if I go down in frequency, let's go way down here. You're going to start to see, it takes a minute for it to propagate out here. We see we have a construct, we call this an antinode, where it's the most positive and most negative, where they're constructive. So this is an antinode, and this is a node. A node is where there's like a null point. So this is what's happening with, this is one of the problems with stereo. So this problem, and this is also one of the good things about headphones. Headphones send one piece of information to one ear. Whereas in this case, we have 2 sound sources going to 2 ears, but they're kind of hitting along. They're hitting different ears at different times, and you're getting constructive and destructive interference, and you have room effects, and it gets really complicated. And this is why we need sound treatment in your room, because not only does this work from speaker to speaker, but it works off of reflections too. Say I have it's the sound coming off my speaker here, and it hits the wall over here. Now I essentially have 2 sound sources. So anytime I have 2 sound sources, active sound sources or even passive, one active and one passive sound source as a reflection, we get these interfering waves with one another, and that's a real problem. So let me make sure I hit what I need to hit on there. Yeah. So and where this lobe is frequency dependent. So when it was like hot, quiet, and actually what's interesting is let me just do this one more time. Bring it up here, do it again. Oops, no, I guess it's 500. Let me bring it up to 1,000 hertz. Do it one more time, and I want you to guess, tell me in centimeters how far apart the null points are. It's a little hard. 15? No,
about 8.
8? Well, it should be about 30. Because remember when we did that calculation? 1 kilohertz wavelength is 34 centimeters. It should be about this. Now the truth is this demo, it's a bit crude because we have room effects here. So you're supposed to be getting 2 sound sources here, but we're also getting reflections, and we're getting interference from all other places. So it kind of mucks it up a little bit. But you get the idea. The idea, though, is it's 34 centimeters. A 1 kilohertz wave is 34 centimeters. So we should have from null point to null point, we should have, or a node to node, we should have about 34 centimeters, plus or minus a little. Again, it's kind of bucket physics, but you get the idea. All right, so let's talk about, where's my presentation? There it is. So let's talk about reflection. Now, reflection of sound waves, I got to go for last spring we went to Moab, and I got to sleep. We went camping, and we were in this cave, and of course being the nerd that I am, I was just enthralled with echoes, and I was just playing with it all day. And especially because my dog, I could call his name, and then it would call over there. It was really cool. So you call his name, and he would look over there as soon as it came from over there, and he'd look over there and look around. So it only lasts. The effect only lasted for about a couple minutes. He didn't catch on to it, but he was like, I'm over it. So, but like, we understand that if we have a perpendicular surface, and I speak at this, it's going to go and hit that. The sound energy wave is going to hit that wave, and it's going to reflect right back to me. And actually, it comes back as an opposite phase. But the idea is that it goes and it hits the wall, and it reflects right back to me. Now that's an easy one to envision. But what if we think about on an angle? If we have a sound source and then a wall, it hits the wall, like me speaking at this wall right here. If we think about it like a beam, it goes down, it hits the wall, and then it's going to go what we call is called the angle of incidence. The incident angle is equal to the angle of reflection. So if I'm at a very steep angle here, it's going to reflect at a very steep angle. Anybody remember Donald Duck Mathemagic Land? I don't know. We used to watch that when I was like elementary school. And it was the pool thing. And they always would show, you can think about like the pool cue. If you hit a ball, the cue ball at a bumper, it's going to reflect at exactly the reflection angle is going to be exactly the same as the incident angle. So the same thing happens with sound. The thing is with sound, it gets a little more complicated because when I speak in a beam, it spreads out. So let me pull up my simulation. Oops, not that one. I got too many simulations going on here. All right. Let me get rid of this one because we don't need this one right now. Plus it's dragging the system down. Okay, come on. Get up there. I've got too many things open right now. Sound wave, come on. Get up there. Okay. Anyway, that one's unnecessary at this point. But the problem is, as soon as we have an incident, we have a sound wave hitting a wall, it comes back and reflects, and now we have essentially two sound sources. So just like we saw before, we're going to have this problem with interference. So this is the argument for dampening, or this is the argument for treating your room. Now, it gets a little more complex because now, remember, we got to think about this as a function of wavelengths too, because the longer the wavelength, as it affects the room, I guess the harder it is to essentially absorb. We're not going to have too much time to talk about standing waves. Let me get back to, sorry, I don't know, when we do, this version of PowerPoint has like, for whatever reason, when you alt tab around, it has like 8 versions of it up there at once, and so I don't even know which is the right one. All right. There's a lag here. Computer's running really slow right now. Have it? Okay. But are we doing on time? Okay. But what I want to talk about more, so we have this idea of reflection, and the sound hits something and reflects off of it. Now that's just talking about a single wall. We talk about it in a room like this. We've got people, we've got surfaces, we've got walls, we've got other speakers, we've got all sorts of stuff for it to reflect off of, and now it gets very complicated. If you're an auditorium designer or a room designer, this is stuff that is very, very important. Now I want to look at this other one, and this is what I want to spend the rest of the talk talking about, is diffraction. Diffraction is huge for what we're talking for our discussion. Let me make sure. So what refraction is, it's the bending of sound waves. Now it's also, when we talk about light, it also bends. You can bend light waves as well. And when you're talking about measuring stars and distances, and you use refraction for all sorts of different things. But in sound, we use the term as bending waves. Now, if I have a microphone on right now, so it's not going to work too well, but if I'm speaking to you right here, and I went down below here, and I keep talking, the timbre changes, or the quality of sound changes, but you can still hear me. Now, of course, there's a lot of reflections going on, so it's helping you hear this, but if I were outside, where there's no reflections, except for maybe if we're on some soft grass, and I put this board up in front of me, in front of my face, you would still be able to understand what I'm saying if I were to go like this. You're like, well, how can that be? Some sound passes through the device, the wall, but for the most part, it's passing around. And it turns out low frequencies bend while high frequencies don't. Now this part maybe not the most intuitive part, but when we think about it okay, let me use that marching band example again. A marching band, when you have the home team, you have the whole band facing you, or when your band is playing, the whole band is facing you, and you can hear the the whole band in its glory. But when you have the band facing the visiting team, you can't hear anything except for mostly you can hear some of the tubas. Now that's, again, there's some reflections going on, but the wavelengths of those tubas are wrapping around and going in the opposite direction. So what we have a case here where high frequencies go straight, act as a beam, and low frequencies bend. Now what is that a function of? Well, if we look at it as, think about it like this. When you get called, maybe you guys don't get called anymore, but it's been a while for me. But when you have a party and the cops get called, it's because the bass is annoying to your neighbors. They don't hear the cymbals of whenever you have the stereo cranking. They don't hear the cymbals. They hear the but it's kind of the classic like party next door sound is a kind of thing, and that's because those low frequencies travel so well. So if I have a very low frequency, now again, let's think about this in terms of wavelength. A low frequency, we'll say 20 hertz, just because we already have that number in our head, that it's 17 meters long. Now most regular home playback systems can't really go down to 20 hertz. They might be do a little bit of it, but most of them can't do that much. But for this argument, we'll say that it is. So if I have this 17 hertz or 17 meter wave, and I have a door that's open right there, this humongous wave is not even going to notice that door is there, that door opening is there. It's just going to pass right on through it and like go all over the place. Because again, my opening is tiny compared to my wavelength. My wavelength is humongous. So if you think about it like this, we've got a surfer here. A surfer sitting on this is surfing. Now again, I'm using a water analogy for a sound one, but you can kind of get the idea here. So Now, of course, a wave is not conscious, but do you think that surfer is having any effect on that wave right there? I mean, he's cutting a little dent in it right here, but for the most part, that wave has he's not changing that wave at all. That wave is massive compared to this little tiny person, the amount of energy that's involved in that wave. And the same thing happens with sound waves. If I have, say, if he were a post, say like a buoy that's stuck to the ground, or maybe a tree coming out of the ground, and that wave comes, that wave will just wrap right around him and keep on going like he never even existed. And that's exactly what sound waves will do too. If I have a 20 hertz wave hit me, that wave is just going to hit me and keep riding, wrap around me and keep on going. It doesn't even know that. Of course, it doesn't know anything, but it doesn't know that I exist, right? I don't affect it at all. Whereas if you think about you have the kiddie pool. You're just sitting in the little kiddie pool, and you start tapping your finger on the water there. These little tiny ripples go along, and they hit you. They're not going to. You're actually going to cast a shadow, an acoustic. Well, you're going to cast a wave shadow. But you can also do the same thing with sound. So if we talk about 20 kilohertz, I've got a 20 kilohertz wave, about this big. Now that 20 kilohertz wave is going to hit me, and it's because I'm humongous. I'm this beast compared to this little tiny sound wave. It's not conscious of anything, but. Well, maybe, but that's a different discussion. So it hits me, and I absorb it, and I turn it into heat. So in other words, if you were standing right behind me, you would hear low frequencies wrap around me, but you would not hear any of the high frequencies. And that's exactly what happens. You can try this demo at home. When you have a speaker playing in another room, and say if it's in your bedroom and you're in your living room, you can hear that there's sound coming through the hallways, and some of that's from reflection, but you'll be able to tell that you can hear those low frequencies a lot higher than you can hear the high frequencies. Same reason if you have somebody who has a really nice hi-fi system down the hall, and you're in another room and they're having it cranking, you hear those low frequencies because those humongous waves barely even, they just wrap themselves through at every opening. So we have kind of two cases where we have a small object and a large wavelength. And then that wraps itself, and it wraps it around and keeps on moving. That's called diffraction. It diffracts around the object. And then we also have a case where we have a small opening and a large wavelength. So say an open window. So if I have an open window, or these doors in the back here, those doors are probably about 6 feet wide by 6 feet, 7 feet wide, 7 feet tall, something like that. That any wavelength that's longer than 7 feet wide is going to diffract and wrap itself around. Any wavelength that's shorter than that 7 feet is going to go in a straight line. So you can figure out, based on the width of the window or the width of the opening, what frequencies will diffract and what frequencies will not. So we've got this other case. How are we doing? Okay, doing about right. Okay, so let me see if I had any other of those. Yeah. Okay. So let's talk about. Let's reel this in, and we all have this sense of diffraction in our real lives, but let's talk about it in terms of maybe something that's applicable to this conference. Or we've got speakers. Now speakers can act like, we can imagine this to be like a hole into, that the sounds were coming through from another room. So what I have here is just a little 4-inch VFA driver. Let me see, am I on right there?
Can you turn it up?
Please. Okay. So what we can do now we're going to kind of try and start tying some of these concepts together. So I have let me, whoops, rookie mistake. Let me turn this one off too. This is the right way to do it. Okay, so let's talk about speakers, and we're going to talk about this this diffraction business first as like how we employ this with speaker design, but also how we can use a little bit with acoustics. So what I have here is I have a driver. Now it's gonna start making these compression waves. Now if we think about it, like if we look at the profile of it, it's gonna be compressing the wave, but at the same time it's gonna be creating a rarefaction wave from the backside of this thing. So we have essentially a radiating pattern of a compression wave. So if we imagine this speaker pushes out this direction, it compresses the air in front of it and sends it out into the wild blue yonder. And then on the backside, it does the same thing with the rarefaction wave. And the rarefaction wave is going to go this way off in the wild blue yonder. But what will end up happening is, we were talking about before, if I start doing a really low frequency, it's going to be able to wrap itself around. So if I talk about a low frequency a frequency that's long wavelength compared to the size of this driver, it's going to wrap around and go back the other direction. So what happened? Well, I guess we've seen that also with wave interference too. So now I have like a rarefaction wave going this way and a compression wave going this way that are going to interfere with each other in opposite polarity. What happens when they're opposite polarity? Cancel each other out. So let me pull up some tunes here real quick so we can. Let me turn that down so I don't blow anything up. All right. Let me pull up Windows Media Player. Just need a song. I tend to always use this tune, but that's cool. Come on, go. Okay. So, read this channel. Okay. So what I have here is it's the speaker's moving back and forth in this direction. Now I'm using the entire frequency range with one. I'm not doing anything like this where we have the crossover and separate drivers. This one speaker is trying to play the entire frequency range. Now, of course, this driver we know can't play very high or very low, but it can do a pretty good job of it. If I turn this up now, as we imagine, it's okay. You can hear it. It's just not that great. So what we're going to do. Now, that's because the low frequencies are diffracting around here. So what I wanted to do is I want to remove those. I want to try and separate those two out so that the low frequencies are going to go that direction and not interfere with the back ones. Well, that's what we're going to use this baffle for. Check this out. Well, what just happened there? We effectively separated the low frequency, like we allowed more of those low frequencies to go in that direction and not wrap around and out there. So that means the larger this baffle is, so it's still happening. It's still diffracting around the backside of this, but it's got to be frequencies that are longer, whose wavelength is longer than this right here. So it would stand to reason that the bigger I make this baffle, the better it's going to work. And of course, that's exactly what happens. That's why we call some speakers infinite baffle speakers. Ideally, what we want to do is I would cut a hole in this wall right here. I'd put my speaker in that wall, and that way I would completely separate the front wave from the back wave. And that's what boxes do. And that's why we have absorption material in boxes, is to absorb the back half of that wave. Now from here we can start talking about all sorts of loudspeaker design theory. But that's not exactly what I wanted to go with here. What I wanted to talk about mostly is how this idea of putting the speaker on here separates the front wave from the back wave. And if we were able to completely cancel that back wave out so it doesn't hit the front wave, that's what a sealed speaker box is designed to do. Now again, when we start getting small enough, that we call them acoustic suspension, and what goes on inside the box does have an influence on the driver here. But for all intents and purposes, that's what's going on there. So we could think of this tiny little. So now what's ended up happening is even though I have this speaker here, and we'll just say it's sealed and all the back waves, so we only have the low frequencies coming out here. But still, low frequencies are going to wrap around themselves and they're going to hit the wall behind them. And they're going to bounce off that wall and act as another sound source and come back forward. And now we're going to have interference. Again, another argument for doing a fair amount of absorption. Because if you want to hear the effects of the room, that's cool. But if you want to hear just the speaker, you need to absorb the other part of that wave. So what's happening is high frequencies are going to come straight off the speaker. Low frequencies are going to diffract around to the back and bounce off the walls there. And when you have multiple speakers, multiple right angles in the rooms, we start getting complicated, and we get this idea. But this idea of, I guess, this difficult model of interference with what's going on through a room. So the idea is that high frequencies are going to come straight off, low frequencies are going to wrap around. And this is something that if you look at when you're shopping or when you're discussing speakers and you look at the off-axis response, you'll often see that the low frequency doesn't change much, but the high frequency does. And that's why. Because if I were to stand right here, the high frequency is going to come off like a beam, low frequency is going to wrap around right here. So with that, let's from there we could start talking what I want to do. It sets the stage for talking more about standing waves and how our room effects, our rooms themselves start resonating, and what we can do about that. But unfortunately, with 1 hour, we don't have a whole lot of time to talk about that. That was kind of just as a safety thrown in there. But from here, if this is something you're interested in pursuing more, or you have any inkling on this kind of stuff, these are two really awesome books on this material. Master Handbook of Acoustics by the late Alton Everest, who's now taken over by Ken Pullman. I actually haven't read the fifth one. I only have the fourth edition. I'm interested to see what's in the newest edition. But this other one, Floyd Toole, came out with this book last year, and I've seen him speak a couple times on this stuff. Awesome, awesome, awesome book. It talks about speakers in rooms, and it gets a little boring sometimes. It's a little technical, but fantastic book. So if you have any interest on acoustics on this stuff, these are two great reads. So with that, I know I was kind of hauling along there, but do we have any questions on any of this stuff that I hit on today? Yeah.
The low frequency, can it actually wrap a complete 180 degrees?
Yes, and so what you do is you can imagine it coming out in a spherical pattern. So we call that 4-pi. And so in other words, it emits in a 4-pi, in a spherical pattern, where the high frequencies can emit essentially in a
Polarization pattern for an antenna?
Not, is it? Oh, okay, yeah. Yeah, I guess if I understand exactly what you mean, I'm a little fuzzy on that area, but yes, I think so. Yes?
How do headphones reproduce low frequencies?
It's a diaphragm moving exactly right here, and it's at 20 hertz. A 20 hertz diaphragm in a headphone is moving at 20. The diaphragm is in fact moving at 20 hertz. It's just coupled very efficiently to your ear because it's right here, and you're also not getting any interference. So the air pressure, especially if you're talking about sealed or open air, the things change a little bit. But either way, you have a diaphragm that's moving very closely to your ear, and so it couples very efficiently to your ear, and so it can reproduce low frequencies very well.
Comb filtering?
Comb filtering. So comb filtering is actually, and I wanted to do some demonstrations of this. So when we have this frequency come off and reflect off the back here, off the back of this wall, it essentially acts as another sound source. So if I were to take the other general mic and put it back here, and I were to sweep it up through the frequency range, some of those frequencies are going to be constructively interfering with each other, and some of those frequencies are going to be destructively interfering with each other based on your position. So at that point, what's going to end up happening is you get, it's called the comb filter because it kind of has a bunch of teeth. It looks like I wish I had a whiteboard. In other words, a comb filter kind of looks like this. And the reason it looks like that is because some frequencies are constructively interfering with each other, and some frequencies are destructively interfering with each other. And it could be either, anytime you have two sound sources, this is going to end up happening. And if you get a chance, you can actually, if you have some sound software, if you just throw a slight delay on one versus another, it's a very interesting effect, and it gives you kind of a hollow, tubby sound. Now, we use that in music for all sorts of effects, but in room acoustics and in hi-fi situations, we typically don't want comb filtering to happen. Is that kind of, I know it's super brief, and if I had more time, we could actually set up some demos to do it. It's pretty neat stuff.
Also, if you have two microphones,
yes.
I was doing TV sound for a while, and if I have microphone first and this microphone later, and I had
Yes.
to close one or the
Yeah.
other because the voice gets all muddy.
Yeah.
with the tongue.
You can hear that on like live TV kind of shows quite a bit, where they're going from the crowd mics to the close mics. But so just like when you have two sound sources, when you have two sound receivers that you sum the effects to, it has the exact same effect, and it's very muddy and annoying to listen to. Yes.
I believe I read a few excerpts of a tool on the internet talking about actually using multiple drivers at multiple locations to actually help correct
Yes.
phasing issues of smoothing response out, especially for low frequencies. Multiple subs and multiple locations to use this problem you're talking about actually to work.
Right, and I've sat on some AES talks where they've done that too, and it's a relatively new, because our analysis software and our analysis means are getting much more sophisticated. We have much better modeling tools than we used to have, doing ray tracing and acoustic design tools. And what they'll find is that, depending on the shape of the room, you'll find that you'll have huge antinodes and huge nodes in different areas of the room. And by using your subwoofer, and we know we have. If some of us use subwoofers, some of us don't. But if you move your subwoofer around the room, it changes sound. And that's not because of the proximity to you to the subwoofer. It's because it's exciting different room modes. And when you have different pockets, especially a non-square room, you're going to have some funky hot spots, in other words. And what you can do is you can use extra drivers, phase flipped or somewhat phase flipped, to kind of control this stuff. And it gets very, very complicated very quickly. But the people who have the tools to use this, like Russ Berger and John Stork, and John Stork I've seen talk a number of times. He speaks at CU, has some pretty interesting software, sophisticated software for that stuff. Yeah.
It seems to me that the chair you sit in, the kind of back you has, is there a lot of research on, or?
Well, yeah, I mean, big time. So, I mean, yeah, of course, if you're sitting in a high back chair, it's gonna have some reflections and some absorption right here. I mean, even when I'm mastering, I can't wear a sweatshirt and I can't wear a hat, because my hat actually makes it, your pin of your ear is a very sensitive device. We used to back in the day, they weren't exactly sure what this business was all about. Turns out this is a very, very complex filtering and location. Again, another talk for another day would be ear and psychoacoustics, which I think is just fascinating stuff. But localization, when we close our eyes and we're able to locate sound, is a function of this. And when you put something else that has a close reflection, it will start to mess with your response in your ears. And even like I said, even your hat, or I can't wear a hoodie. I mean, I could probably get away with this jacket, but typically when I master, I wear just either a t-shirt or a polo or button-up kind of thing. I can't wear anything heavy. Yes. Uh-huh.
And you have crossover, let's say 1,000 to 3,000. How does that phase?
Well, I mean, crossovers can get a little tricky, but what they're saying is, when you cross over, say 3,000 hertz, what it's saying is that the mid frequency between those two drivers is crossing over, and then you also have the steepness of the curve. So the most modern speakers use Leibniz-Riley, which is a 24 dB per octave slope, and what they're doing is it's a very steep slope. So this gets deeper into diffraction speaker theory, but the steeper the slope, the less crossover. So if I have this crossover at a very we'll call it first order, 6 dB per octave, where there's a lot of overlap between this speaker and this speaker, you're going to get a lot of interference and a lot of lobing from this speaker to this speaker. But if I do a very high order, say 48 dB per octave, where this one plays down to a very frequency, then cuts off very sharply, and this one plays up to a certain frequency, cuts off very sharply. They have very little interference with each other. They have very little interference, which is a good thing. You're like, okay, that's exactly what we want, right? But now all of a sudden, when I move off axis, I get very, very weird effects. So most loudspeaker design has a lot to do with compromise. You can either have good transient or you can have good frequency response. And same thing happens when you're choosing your crossover. You can either have fantastic on-axis response and with very little lobing, but then you can have terrible off-axis response. So it's a matter of what's most important to you. Do you want good general response of the speaker, or do you want very good exactly on-axis response of your speaker? So when you're looking at crossovers, and when they cross over with each other, essentially what they're doing is saying where the frequency is crossing over, and then you have to read the specs usually and find out how much of the slope of that crossover frequency and how many frequencies are crossing over. So some people like first order crossovers, some people like 24 or fourth order crossovers. It gets a little bit more complicated and probably outside the scope of what we have to talk about right now, but it is very interesting stuff. So I apologize. It gets a little heavier than what we have time to talk about right now. Yes?
If I understood correctly, you said that waves travel at the same speed,
Yes.
irrespective of the frequency.
Correct.
In a lot of speaker designs, they talk about time alignment.
Yes.
And they will move the tweeter relative to the woofer.
Exactly.
All of those, if they're traveling at the same speed, why wouldn't they be going 20?
I should have addressed that. That's a very good question. We'll have to probably wrap up after this because we got to get going here. But one of the things that you'll see, and when you're walking around and you're looking at a lot of these speakers, you'll see the baffle on a lot of them are slanted back. Like it kind of looks like they're sloping back, right? Or you can see on some speakers, now these ones are not necessarily time aligned, at least not physically. They may be done electronically time aligned, but physically what we do is when you have a driver, and if we're talking about a bigger one here, where do you say that the sound is emitting from? Is it emitting from where my hand is, or is it emitting from where the dust cap is right here? And when we're talking about something like this, where the dust cap is set pretty far back, maybe compared to this tweeter, which is a little farther forward. Now, in that crossover region, if they're playing the same frequency, they're emitting the same frequency. So if I have, in case of this, my tweeter's sitting further forward than my woofer, and if I turn on the side here, and I imagine them going like this, exactly in phase with each other, now what we do is we have two waves coming off the front of these drivers, but they're somewhat out of phase with each other. Now, just like we saw before when we saw those two speakers, and we saw that there were nodes and antinodes, if you have two speakers that have now, they're going to be there's going to be this node and antinodes no matter what you do. But the idea is if you're straight on with the speaker right here and they're time aligned, that you'll be in where an antinode is and where you're going to get good response. Now, if you move up and down right here on this axis, you're going to get those nodes and antinodes. And it's only going to be in the crossover regions, and it's going to be variable. So it gets very complex very quickly. But what you're doing is, what they can do is if they slant the speakers back so that the center point of this driver and the center point of this driver are exactly in the same point, they're essentially time aligned. And so they emit those frequencies at exactly the same time if you're sitting right here. So you got to for that to work, you have to sit exactly right in front of the speaker or like in a certain other spot. But for the most part, most speakers are intended to be listened, pretty much straight from the back of the speaker. If I have it set up here, it's not going to work as well. Maybe if it's aimed down at you. But the idea between time aligning is you actually physically put the speakers in so that the centers of those drivers are exactly the same. Now you can also do this electronically. I could put a little bit of a delay on this one right here, and so that this sound came out later than this sound, and they came out time aligned that way as well. Cool. I think we probably better wrap up here because we got the next crew coming in here. But thank you guys so much.